Alright guys, so I have drawn the trajectory of an object that was launched at an angle. And so this is different than what we've seen before. But the good thing is, in terms of physics, we're going to see a lot of the same themes, a lot of the same ideas pop up. But there's just a couple of new things that will change. And since we've been practicing how to say certain things, we're just going to change the way we say certain things and the way we perceive them. But at the end of the day, I mean, it's really a very similar type of motion. So I'm going to try my best to explain to you what that looks like. So what happened originally is this object was launched at, say, this angle. Okay? And so it was launched with some initial velocity. But the reality is we don't like talking about things that are in this kind of format. We like when things are in an x, y format, right? X being here and y being there. In other words, we like to look at the components of, say, something that would be like this, right? This is made up of x, y, and we don't like that. It's just not simple enough for us to really say what we need to say about the physics of this kind of motion. So this object was launched at an angle, but what we should see as physicists, as good physicists, is we should see this. We should see that it has a horizontal component, which we would call Vx, and there is a vertical component, which we would call Vy. Okay, and the reality is we know that as we move forward, the object would go something like this, right? The vectors would look like this. But we're gonna actually break it down and keep talking about it in terms of its components. So I'm gonna stop drawing those green arrows, which we would call the resultant arrows, for my fancy pre-cal people and calculus people. But we just want to think about components, and so I'm gonna leave my components in red and blue, and you can see I've already started a pattern here. Any arrow drawn in red will be a y component, the vertical velocity, and any arrow drawn in blue will be the x component, Vx. And what I want to point out first, which is the easiest thing, is we know that the horizontal motion will not change. There is nothing pushing or accelerating. There's nothing pulling or accelerating. This object is going to keep moving sideways at a constant speed, or we could even say a constant velocity. And what that means for my diagram is that all my arrows, as best as I can do it, will be the same length when they are blue arrows that represent the horizontal component of motion. These are all labeled Vx. Notice that they are all, to the best of my limited artistic abilities, they are all the same length. Okay, I want to redraw that one a little bit. Okay, they are the same length. Why are they the same length? They're the same length because the velocity in the horizontal component is constant. It is moving at a constant speed in the horizontal direction. Okay, notice I said that two different ways. The velocity of the horizontal component is constant, or I could say the object is moving at a constant speed in the horizontal direction. At the same time that it's moving in the horizontal direction, it is also moving in the vertical direction. However, this is where things look a little different. And I actually want to start at the peak. If you remember, something very special happens when something is falling. So this object moves up and then starts to fall. So what happens when an object starts to fall? Okay, it's doing nothing else but starts to fall. What can we say about the vertical velocity when something starts to fall? Well, that was a tough question, but what we should be thinking about is that the vertical velocity when something starts to fall is 0 meters per second. Right? I'm ignoring the start. I'm ignoring the first part of this motion because I know that we know a lot about what happens here. What happens after an object starts to fall? What happens to its vertical velocity? Well, we know this. It starts to fall and gain some speed, and then it has more speed, and then it has way more speed. Okay, so let me draw this one even shorter just to really exemplify that. Okay, so we have no vertical speed, then we start to speed up, and the way I show that is that my vertical arrows, which represent the vertical velocity, Vy, they start to get longer. Well, guess what? If you look over here, it's the exact opposite. And what I mean by that is the arrow that I drew on this right side is going to be the same length arrow that I draw on this left side, except that it's the other direction. Why is that? Well, the object is moving up. So it has to have a vertical velocity if it's moving up. And while it's moving up, these arrows get smaller. But what is the reason why the arrows would get smaller? What would be something that would change the velocity in the vertical direction? Well, it's our best friend, gravity. The gravitational acceleration, little g, is in the negative direction. So this is what's going to slow down the vertical velocity, but once it reaches the peak, once the object reaches the peak, it's actually what's going to be what speeds up the vertical velocity. Okay, so if we backtrack, here's what happens. The horizontal velocity is constant, but the vertical velocity slows down, then speeds up. Okay, slows down till we get to our peak, and then speeds up till we land again. Okay, the other thing that I want you to keep in mind is we do have a number for little g. Little g is 10 meters per second squared, but we also know that it's in the negative, so we call it negative 10 meters per second squared. Okay, that's the reason why these red arrows cannot remain constant, because this is changing the vertical velocity. And then the other thing, and you can't see this, and if you don't know vectors that well, you definitely are going to struggle to see this for just a little bit, but I just need you to believe me on this. The object will land at the same speed that it is launched. Okay, if you think about that, what happened from the launch to the land? Not much in terms of changing. If we ignored everything else, nothing really changed. The horizontal component is still the same, okay, as it was when it started. And the vertical component is the same as well. The only difference is that it's in the opposite direction. So I need you to remember this, that the object lands at the same speed that it was launched. Okay, this is a new idea, but I want you to know that.